In chapter 1.5, we're going to look at applications of quadratic equations. Our objectives in this chapter is to solve application problems using the quadratic equations in geometry. And our second objective is to solve application problems using quadratic models. Example 1. Dimitri is having a fish tank constructed to fit a niche in his wall. The width must be 12 inches, while the length is twice the height decreased by 8 inches. The total volume of the tank must be 8,840 cubic inches. What are the dimensions of the tank? So in this problem, we set up the height as h, and our width we know is 12 inches, and our length is 2h minus 8. Our strategy in this particular case is volume is equal to length times height times width. We can plug in the information from our problem into the strategy. 6,840 is equal to the length, which is 2h minus 8, parentheses. The height is h, and the width is 12. We can divide both sides of the equation by 12, and we get 570 is equal to 2h minus 8 times h. When we distribute the h, we get 2h minus 8h. Again, we can divide both sides of the equation by 2, and we get 285 is equal to h squared minus 4h. Now we're going to complete the square. So from the 4h, we can take the 4, we can take half of it and square it and add it to both sides of the equation. And we get this. We get 4 plus 285 is equal to h squared minus 4h plus 4. Well, we have a perfect square on the right-hand side of the equation. We get 289 is equal to h minus 2 squared. And now we can take the square root of both sides, and we get a plus or minus 17 is equal to h minus 2. We notice that the negative 17 isn't going to work here because you can't have height as negative. So we have 17 is equal to h minus 2. We add 2 to both sides, and we get h is equal to 19. And we put all this information back in, and our dimensions is h is equal to 19. The length is 30, and the width, of course, is 12. So in our problems, our geometric problems, we're going to have problems that have areas to them. We may see problems with parameters, maybe not in this particular case. And we're going to see problems with triangles, either with areas or using the Pythagorean theorem. So we're going to continue our example 1 of the gallons of water for the tank. If 1 gallon of water is measured to be 231 cubic inches, and the weight of 1 gallon is 8.345 pounds, what will be the weight of the water in the tank? Well, we have to break this up into two pieces. One is, we know that this is the strategy. First of all, 1 gallon is equal to 231 cubic inches and is equal to the weight of 8.345 pounds. So now we calculate the number of gallons first, and we see that it's equal to 6,840 cubic inches times 1 gallon to 231 cubic inches. The cubic inches cancel, and we divide 231 into 6,840, and we get approximately 29.61 gallons. Now we take the gallons to find out how much weight we have, since each gallon is equal to 8.345 pounds. We multiply that by 29.61 and we get a total of 247.10 pounds. So in practice skill 1, a box is to be formed by taking a sheet of cardboard and cutting away 4 2-inch by 2-inch squares from each corner, and then the sides are turned up to form a box that holds 56 cubic inches. If the length of the original piece of cardboard is 3 inches more than the width, find the dimensions of the original piece of cardboard. So we notice that indeed we have x plus 3 as our length. X is our width. We're going to use the strategy, the volume is equal to the length times the width times the height. And so in this case, the length of our volume of the box after we cut out the pieces is going to be x plus 3 minus 4. The reason it's minus 4 is because we have 2 inches on either side of the length. And then we have 2 inches as the height, because that's the way the box is going to be constructed. And then finally we have the width is going to be x minus 4. Again, there's 2 inches on either side, and we have to take those 2 inches off when we construct the box. So we plug this information into our formula, right? So 56 inches is equal to x minus 1 times x minus 4 times 2. We divide the 2 out and we get 28 is equal to x squared minus 5x plus 4. We use the zero principle. And we have 0 is equal to x squared minus 5x minus 24. And we see that it is factorable into 2 parts. One of the factors is x minus 8, the other is x plus 4. And we set it equal to 0, so we see that we can set x minus 8 is equal to 0 and x is equal to 8. The other factor doesn't work because x would be equal to a negative 3, and we can't have a negative 3 as far as our dimensions are concerned. So our final dimensions, when we plug it back in to the original information, we get, actually we get this right here. We get the length is equal to 11 inches and the width is equal to 8 inches. So now we get to look at the Pythagorean theorem. 3 sides of the right triangle are represented by 3 consecutive integers. What are the integers? Well, our strategy, of course, is the Pythagorean theorem. And we have our triangle here, which is set up with A is one side, B is the other side, and our hypotenuse is C. So in this case, we're going to let A equal x, B equal x plus 1, that's the next number in the consecutive integers, and the third consecutive integer is x plus 2. We plug that into the Pythagorean theorem, and we get x squared plus x plus 1 squared equals x plus 2 squared. We FOIL out the information, and we get x squared plus 2x plus 1 is equal to x squared plus 4x plus 4. The x squares cancel, one of the x squares cancel. We're left with x squared plus 2x plus 1 on the left hand side, and 4x plus 4 on the right hand side. We use the zero principle again, and we move everything over to the left hand side. We get x squared minus 2x minus 3 is equal to 0, and we see that's factorable into 2 pieces. X minus 3 times x plus 1. And in this case, the x cannot be -1 because we can't have a negative length, so x must be 3. And so A is 3, B is 4, and C is 5. So we have another area problem. As the minute hand on the face of a clock sweeps around once, it covers an area of 114 square inches. What is the length of the minute hand? Round your answer to the nearest inch. Well, here we get the area is equal to 2 pi times r squared. That's our strategy. We divide, we just put the information in, so we get 114 is equal to 2 pi times r squared. We're solving for r, so we're going to divide both sides of the equation by 2 pi. So we get 114 divided by 2 pi is equal to r squared. We can take out the 2 and we get 57 divided by pi is equal to r squared. We take the square root of both sides of the equation. We get plus or minus the square root of 57 over pi is equal to r. The negative square root doesn't work, so when we take the square root of 57 over pi, the positive, we get approximately 4.26 inches. If we rounded it to the nearest inch, it would be about 4 inches. So now we are looking at triangles from an area standpoint. So skill practice 2, a large stunt kite is in the shape of a diamond with a small upper triangle and a larger lower triangle. The total area of the kite is 36 feet squared. The value of x in the figure represents the base of each triangle. The height of the lower triangle is 2 feet less than the base. Find the base and the height of the lower triangle. So we use our strategy here. Our strategy again is area of a triangle is equal to 1/2 the base times the height. So we've already got our problem relatively set up in our diagram. We have the lower height of the kite of the lower triangle is x minus 2. The height of the upper triangle is 3 feet, and the base of both of those triangles is x. So the upper triangle, we can set that up. Upper area of the triangle is 1/2 x times 3, which is going to be 3/2 x. The area of the lower triangle is 1/2 times x minus 2 times x, and when we distribute the half, we get 1/2 x squared minus x. Now we have to look at the total area. The total area is the upper triangle plus the lower triangle, and so we substitute that in, and we get 3/2 x plus 1/2 x squared minus x. What we're going to do here is we set it up. We have 36 is equal to 3/2 x plus 1/2 x squared minus x. Now I'm going to multiply through by 2 because I want to get rid of the fractions. So when I do that, I get 72 is equal to 3x plus x squared minus 2x. And I combined the x's, so I end up with 72 is equal to x squared minus x. We use the zero principle, and we subtract both sides by 72. We end up with x0 is equal to x squared minus x minus 72. This is factorable into two factors. We get 0 is equal to x minus 9 times x plus 8. We see that the negative x will not, or the negative 8 will not work in this problem. So x is equal to 9 feet. So the base x is equal to 9 feet, but the height of the lower triangle is equal to 7 feet. So we have another triangle problem, except this one we will be using the Pythagorean theorem. A sail on a sailboat is in the shape of two adjacent right triangles. The hypotenuse of the lower triangle is 10 feet, and one leg is 2 feet shorter than the other leg. Find the lengths of the legs of the lower triangle. So we're going to use the Pythagorean theorem. Here it is. A squared plus b squared is equal to c squared. So in this case, I'm going to let a equal x minus 2. And b is going to be x, and c, of course, is 10 feet. So we plug that information into our Pythagorean theorem, and we get 10 squared is equal to x minus 2 squared plus x squared. We FOIL out the x minus 2 squared, and of course we square the 10. So we get 100 is equal to x squared minus 4x plus 4 plus x squared. And so we can add the x squares together, and we get 100 is equal to 2x squared minus 4x plus 4. We can divide out a 2 on both sides of the equation. We get 50 is equal to x squared minus 2x plus 2. We can subtract 50 from both sides eventually and use the zero principle, which is 0 is equal to x squared minus 2x minus 48. We see that thing is factorable into two pieces, which is x minus 8 times x plus 6. And when we let each factor equal 0, we see the only one that works is x is equal to 8. And so x, the base part, is 8 inches, and the A part, the A leg part, is 6 inches. So we're now going to solve applications involving quadratic models. Solving quadratic equation problems. So in example 6, the average weekly earnings, E in dollars, for a group of workers can be approximated by E is equal to 0.12 x squared plus 7.8x plus $555, where x represents the number of years since 2004. So our domain is limited. So our domain is x is greater than or equal to 2004. Now, the issue is you're not going to put 2004 in. We're going to let x for this situation be 0. So at 0, when x is 0, our group of workers earn approximately, on average, $555. So it says determine the average weekly earnings in 2007. Well, the difference between 2007 and 2004 is 3 years. So we're going to let x equal 3 years. When we plug that into the formula, right, we let E is equal to 0.12, 3 squared plus 7.8 times 3 plus 555. And when we end up doing the calculation, we get $579.48 is the average earnings in 2007. Now we're asked the question, in what year will the average weekly earnings reach 638? So now we're going to solve for x in this particular case. So E is 638. So when we put that into our equation, we get 638 is equal to 0.12 x squared plus 7.8x plus 555. Again, we use the zero formula to get it into a quadratic form. So we get 0.12 x squared plus 7.8x minus 83, that's all equal to 0. And now we can use the quadratic formula and set up a, b, and c. So A is equal to 0.12, B is equal to 7.8, C is equal to negative 83. When we plug that into the quadratic formula, we get x is equal to a negative 7.8 plus or minus the square root of 7.8 squared, which is 60.84, plus 4 times 0.12 times 83. And you'll notice that the negative went away because we had a negative 4 in the quadratic equation, divided by 2 times 0.12. So now we have a negative 7.8 plus or minus the square root of 100.68 divided by 0.24, and that's approximately 7.8 plus or minus 10.034 divided by 0.24, which gives us approximately 9.3 years, which we'll just round to 9, and we add it to 2004, and we get the year 2013. In some of our problems, we're going to be looking at vertical position for an object traveling upward or downward under the influence of gravity. So if an object has an initial vertical position of s0 and the initial velocity v0 straight upward or downward, then the vertical position s of the object is given by s is equal to 1/2 gt squared plus v0 t plus s0, where g is the acceleration due to gravity. At sea level, gravity is 32 feet per second squared, or 9.8 meters per second squared, and t is the time traveled. So depending upon how our velocity is measured, we will use one or the other. So in example 7, an arrow is shot from a height of 6 feet straight upward with an initial speed of 20 feet per second. It says write a model to express the arrow's height in feet above the ground after t seconds. So here is our formula that we're going to be using. S is equal to 1/2 g t squared plus v0 times t plus s0. G in this case is going to be 32 feet per second squared, and v0 is 20 feet per second, so s0 is 6 feet. So we plug all this into our formula, and we end up with S sub t is equal to 1/2 32 t squared plus 20t plus 6. And now, of course, we do our little math, and we get S sub t is equal to minus 16t squared plus 20t plus 6. So that is the model that expresses this particular arrow shot from 6 feet straight upwards with an initial speed of 20 feet per second. Now the question asks, how long will it take the arrow to land? So we notice that to land, S sub t has to equal 0. So here's our original formula. We set S sub t is equal to 0. We get a negative 16t squared plus 20t plus 6 is equal to 0. We divide both sides of the equation by a negative 2. Divide by negative 2, both sides. And we get 0 is equal to 8t squared minus 10t minus 3. Now this thing is factorable. It's factorable into two pieces. 4t plus 1 times 2t minus 3. When we set those equal to 0, we get t is equal to a negative 1/4, which doesn't work because you can't have a negative time. But the other one does work. T is equal to 3/2 t seconds, which is approximately 1.5 seconds. So that concludes our chapter 1.5. Please go over the problems in the lecture notes, and we will be discussing some more equations in chapter 1.6.